Okay, so while Kc is good for things you can measure the concentration of, it's hardly useful or practical when you're trying to do it for gases or when you're trying to figure out pressures of different gases. And there are two things that are important there. When we talk about gases, gas particles are moving around all the time. And usually at equilibrium, their concentration at a single point is not the same as the concentration otherwise. So it's really important that we find partial pressure of a gas to figure out what its role is in the whole equilibrium. So for gases, a better way of measuring the equilibrium is instead of Kc. Kc is practical, you can do it, but a better way, a more practically useful way is using Kp. Kp is basically pressure constant. It is a constant that depends on the partial pressure of the gas. Now, the term partial pressure means that it is the pressure of that part of the gas. Like, for example, if I talk about air, it has 78% nitrogen. So the partial pressure of nitrogen is 78% of the pressure of the air. So if my atmospheric pressure is 100,000 pascals, the contribution of nitrogen in that is 78,000. Similarly, if my oxygen's concentration is 21%, then its contribution to the atmospheric pressure is 21%, or 21,000 pascals if the pressure is 100,000 pascals. So partial pressure allows us to figure out that what is that portion of the gas, what is its ratio to the total volume. So the partial pressure idea is really simple. Partial pressure compared to total pressure is the same as moles of one gas compared to total moles of gas that you have. All the gases in a mixture, you figure out their total moles, and whatever gas you have, moles of gas, nitrogen, moles of oxygen, moles of carbon dioxide. And this thing is basically called mole fraction. It's a fraction of that particular portion of the gas, that particular gas, compared to the total moles that you have. So mole fraction can be equal to the partial pressure of that gas divided by total pressure. So in basically what we're saying, hidden agenda over here is that the pressure depends on number of moles. Okay, and that comes from Avogadro's law, which we studied in states of matter. So what we're basically saying is, if you have more particles of any particular gas in a mixture, the pressure because of that particle, number of particles, or pressure because of that gas will be higher. So the gas that is responsible for the most number of particles is responsible for the greatest number of collisions, and obviously the greatest percentage of the pressure. So that's the idea here. So that makes it really easy to figure out the K for different gases, especially if you have a mixture of gases, because it allows us to easily calculate. Again, the units depend on whatever the Kp is. So here's how we do it. So Kp is slightly different from Kc in terms that in Kc you use to write square brackets for concentration, but in Kp you won't do that. So let's take the same example as the one that we had in Kc. So we had A reacting with B, making C and D, and the moles were W, X, Y, and Z. So in case C, you had C power Y concentration and D concentration power Z divided by B concentration power X and A concentration power W. But this time you're not going to do that. For Kp, you will take gases and you will take their pressure. So we'll say pressure of C to the power Y times pressure of B to the power Z divided by pressure of A to the power W and pressure of gas B to the power X. And that's it. That's it. And the units obviously depends on what the units of pressure are and obviously what powers you have. So let's do a simple question. The method is still the same, slightly different in terms of that now you will have to figure out the mole fraction before you're able to find the partial pressure. Okay, again, the pressure of any one gas comes from the partial pressure of that thing. And let's do a question and you will understand. Calculate the partial pressure of sulfur dioxide in a mixture containing this. Partial pressure depends on mole fraction, so I'll need the mole fraction. So this one's actually really easy. How many moles of gases do I have? So total moles. I have 0.016 sulfur dioxide, 0.0083 oxygen, and 0.15 SO3. This is an example we were working with yesterday. So if you add it all up, I think this comes out to be 3 here, then 8, sorry, not 3. Yeah, it is 3, then 8 plus 6 is 14, so 4, 7, and 1. Yeah, 0.1743. That is the total number of moles I have. Now, out of that, how much is sulfur dioxide? Sulfur dioxide is 0.016. So, mole fraction of sulfur dioxide is basically 0.016 divided by 0.1743. That is the percentage of or ratio of sulfur dioxide in there. What is the partial pressure? So, pressure of sulfur dioxide is going to be this mole fraction 0.016 over 0.1743 multiplied by the total pressure I have 7, and there you go, that's it. Okay, if I want to do it for pressure of oxygen, sure, oxygen is 0.0083 divided by the total moles, this is mole fraction, multiplied by 7 to figure out the pressure of oxygen, and then same for sulfur trioxide, I have 0.15 sulfur trioxide, 0.1743 times 7, and that gives me the partial pressure. Now let me say that this has a value A, this is B, this is C. So how do I find Kp? Really simple. I just find the equation K. Sorry, what's happening here? Keeps coming back. So I find Kp. Kp is pressure of sulfur trioxide squared divided by pressure of sulfur dioxide squared plus pressure of oxygen. Oh, sorry, times pressure of oxygen. So this is going to be C squared or B squared times A. And that's my answer. Now, obviously, the units, this is pressure squared divided by pressure squared times pressure. This cancels out. I have the units of one pressure. So what was the unit of pressure? This is ATM. So I go 1 over ATM or ATM minus 1. So that's how I find Kp. We will need a calculator. So if you don't have it, go get one. I don't have it, but I can't go get one. Okay. So let's take another example of this. Any questions so far? It's a pretty straightforward process. So if you have any questions. Okay, so when phosphorus pentachloride was heated to a temperature T, it breaks down, decomposes to give me PCl3 and chlorine. Super important reaction for halogen alkanes. We use this all the time over there. So what is the Kp? Let's try to figure that out. So how do you do this? Again, first figure out what gases you have and the Kp that you need. So you have pressure of PCl3 times pressure of Cl2 divided by pressure of PCl5. Okay, pretty straightforward. The unit is going to be pressure times pressure over pressure. So this cancels out. I'm left with just pressure, which is ATM. So that's my unit. Okay. Now let me write the values. PCl5, PCl3, Cl2. What do I have? I have 78% of it decomposed. Okay, so what is the mole fraction? So 78% is decomposed. So let me assume that I have 100% in the beginning. Okay, so if I have, again, ICE. Okay, so how much do I have in the beginning? Let me assume 100%. That is 1 I have in the beginning. And 78% is consumed. So that is 0.78. So how much do I have left over? 1 minus 0.78. That is 0.22. Okay. Now, judging by the equation, one of this produces one of this plus one of this. That means if I had 0.78 used up, I have produced 0.78 of this and 0.78 of this. Notice that this thing over here will determine how much of this is present or how much of it is created. Okay. So initially I had 1 mole of PCl5, 0 of this, 0 of this, but at equilibrium, because 0.78 has been used up, I create 0.78 of PCl3, 0.78 of chlorine. So this is the moles or the ratio of moles that I have because I don't really have the numbers. So what is my total moles now? Now, this is where I find the mole fraction. So mole fraction is going to be, I will need the total moles or 0.78 plus 0.22 is 1, then 1.78. That's my total. So my mole fraction is 0.22 over 1.78. This is 0.78 over 1.78. And this is 0.78 over 1.78. Now, what is my total pressure? 2.2. So what's my partial pressure? So pressure of these gases. Partial pressure we show by small p. So partial pressure of PCl5 is going to be 0.22, the mole fraction, multiplied by total pressure, which is 2.2. This one is going to be 0.78 over 1.78 times 2.2. This one is going to be 0.78 over 1.78 times 2.2. And that gives me the partial pressure. I don't have the value, so can you calculate them for me, please? So I got it for this one. This is 0.9640. So 0.9640, I'm sure they be wohi hoegi. My value is a little off for the other one. Can you figure it out? So, up say here 0.2719. Okay, so I'm getting 0.2719. Okay, so that's the partial pressure. Kp mere paas hai. Kp is going to be pressure of PCl3 times pressure of Cl2 divided by pressure of PCl5. I plug in the values 0.9640 times 0.9640 divided by 0.2719. And there you go. I found my Kp. Again, Kp tells us a general idea of which side the equilibrium is favoring. If it has a value that is higher than 1, it is favoring the product. If it has a value smaller than 1, it is favoring the reactants. Okay, so let's try this question. Yeah, so I'll try to solve this and hopefully we'll get a value that we all agree with. So what I'm going to do now is, nitrogen, hydrogen. So this is the scenario. We want to figure out the ICE part first. So ICE, 1 mole of nitrogen, 3 mole of hydrogen. The total pressure is 8 into 10 power 6. And it was contained to find 0.7 moles of ammonia. So 0.7 mole of ammonia is made. Now, this is the important bit. Because 0.7 of ammonia is made, that tells me how much nitrogen is used up. Now, the ratio of nitrogen and ammonia is 1 to 2. That means half of 0.7 is the nitrogen that was used up. So half of 0.7 is 0.35. One way to do this is think of this as 0.70 and half of 70 is 35. So you can easily do it. Now you have the number of moles of nitrogen that was used up, that reacted to make this ammonia. And 3 times that will be the hydrogen that reacted to make this. So 3 times 0.35 is going to be 105. So yeah, 1.05. Okay, now we just subtract them to figure out how much of it is used up. Because notice that 0.35 moles of nitrogen is used up. So you're left with what? 1 minus 0.35. So that is 0.65 of nitrogen that you're left with. Similarly, if 1.05 of hydrogen is used up, you're left with 3 minus that, which is 1.95 of hydrogen that you're left with. Okay, now I need to figure out their partial pressure, and I will quickly go through the mole fraction thing. So their partial pressure is going to be the total moles I have, which is basically 0.65 plus 1.95, which is 2.6, plus 0.7, which is 3.3, and that's the total moles. Okay, so partial pressure is going to be 0.65 over 3.3 times the total pressure. Total pressure is 8 into 10 power 6. Okay, similarly 1.95 divided by 3.3 into 8 into 10 power 6. And lastly, 0.7 over 3.3 into 8 into 10 power 6. You will get values for partial pressure. And now to find Kp, all we have to do is take pressure of ammonia squared divided by pressure of hydrogen cubed times pressure of nitrogen. Plug in the values and you have your Kp ready. So we are going to do a few more examples of this, and I will share those examples with you. So if you have any questions, to wo clear ho jayenge. But one thing before we go on to the practice part, remember that the value of K tells us a lot about the extent of a reaction. So for example, if the value of K is large, it is greater than 1, it means that equilibrium is favoring the right side, it is very well towards the right side. If the value is small, it means it's not really going towards the right side if it is less than 1. And if it is 1, that means the equilibrium is halfway, like 50% of the reaction is done. Okay, so reactions that are fast, they have a very high Kc or Kp. Reactions that are slow, they usually have a lower Kc or Kp, but that does not mean that the reaction is slow because of that. But it just gives us an idea of how the reaction is proceeding. A reaction that doesn't really occur, it will have a very, very small, less than 1 uh, Kc or Kp. So for example, you take lead carbonate, it doesn't dissolve in water. So the moment you add it to water, it creates an equilibrium of these ions mixing together and all that. It doesn't dissolve to a very small degree. That is what it dissolves. So your Kc will be a very, very small value. And if you take water in regard to that reaction, water will spoil the whole value. So we usually avoid adding water whenever we use solubilities, whenever we use Kc. But आपने ES के लिए, whenever you're not talking about ions, you're talking about molecules, we will take into account molecules of water. But if you're talking about ions, we will usually avoid adding water there. Okay. Similarly, if you have a pure solid, you have a pure liquid, its concentration doesn't really change. So whenever you have Kc, don't write pure solids. Don't write those in your Kc expression.
Sir, I said, can you repeat this whole ion and solid thing?
Oh, I was saying that if you're writing Kc for ions, like we will study that in A2, but in that regard, we try not to write water because water is usually much larger in quantity compared to whatever ions you have. So the whole KCKB value is just thrown off. So हम water लिखते नहीं हैं, we avoid writing water. But for Kc for molecules, we do write water because वो water molecule है, ठीक है चलता है. Similarly for Kp, we do the same thing. For steam वगैरह हम लिख देते हैं. But in both of them, Kc and Kp, we don't write pure solids, pure liquids. तो अगर आपके पास कोई भी प्योर सॉलिड है तो वी वोंट राइट इट इन Kc बिकॉज उसकी कॉन्सेंट्रेशन तो चेंज होनी नहीं है. इट्स वॉल्यूम इज नॉट चेंजिंग, इट्स नंबर ऑफ पार्टिकल्स नॉट चेंजिंग. तो सॉलिड्स को नहीं लिखते. फॉर एग्जांपल इफ आई गिव यू this equation and I ask you to write its Kc, like CaCO3 breaks down to produce carbon dioxide and water, carbon dioxide and calcium oxide, then this is a solid, this is a solid, so its Kc is simply CO2's concentration. That's it. Similarly, its Kp is again just CO2's pressure. No need to write the square brackets. Okay. So its pressure is just the pressure of carbon dioxide. Because the solids are emitted, you don't write them whenever you're writing Kp or Kc. Okay. So yeah, we are going to do a few questions for the remaining part. If you want, I can send the picture in the. I'll just post them here. So अपन को attempt कर लो. And if you have any questions, I'm here to answer.
Sir, is partial pressure just for gases or can it be for liquid as well?
Partial pressure is just for gases because for gases, the number of moles affect the total pressure you have, and the rate of reaction of gas or the equilibrium is also affected by number of moles. Liquids वगैरह में इससे फर्क नहीं पड़ता क्योंकि pressure liquids के rate को फर्क नहीं पड़ सकता, मतलब उसको affect कर ही नहीं सकता pressure. So ये दो question है, try to solve them. There's the third one and that's it.